We're looking at FreeRTOS today, which is a real-time operating system, and it's pretty small, so we should be able to get a fairly good idea about what's going on with it, what makes it go. Before that, I have two quick announcements. One is that last week we made it over 7,000 subscribers, which is awesome, but unfortunately 7.29K is not a power of two. So I'd like to see if we can get over 8,192. The other is that starting now, I'm going to temporarily put a pause on taking requests for videos. At this point, I have over 60 requests, and at a rate that I'm currently going, which is about one video a week, that would take me well over a year to get through all of the current backlog. So what I want to do now is just put a pause on taking new requests. I'm going to think of creative ways to get through the backlog more quickly, possibly record some of these offline instead of live, maybe do some shorter videos for smaller repos, and also possibly batch together related repos so that we can see how they're related as we go through them. And then I'm working on what I want taking requests to look like in the future. Once I unpause it, there will probably be something like a Patreon tier for requesters, and then in terms of setting the schedule, what people want to see, I'm thinking that might be done through something like voting or polling on the Answer Everywhere Discord channel. The link is below, or some other mechanism. So that's where I am now. Apologies if there's something you want to see and you just didn't make the cutoff, but I have to do something to make sure that I'm not, that the backlog isn't limiting my ability to give a kind of curated look through the world of open source as I'm trying to do. All right, so that's that. Here is FreeRTOS. I may have mentioned everything is in C. There's some assembly. One thing I've noticed already, I've opened a few tabs just to get things rolling. One thing is that I think it makes sense to look at the portable.h header and include, because this seems to be the mechanism by which, if you want to make FreeRTOS work on a particular chip, that this is the entry point. This is essentially the API that you have to implement. So let's take a look at portable.h, and then after we look at that, we'll take a look at probably just one file in the portable directory, which will be in actual implementation of the portable.h API, if I'm understanding correctly. All right, so this part I think we're going to go through a little bit quickly because we won't really have an appreciation for like what these. We're going to see a bunch of symbols, like for example, these macros, port, byte alignment, etc. We can most likely infer what they're doing, but I think the real way to understand them is to see how they are used through the rest of the code base. So as we're reading, for example, how queues work or how timers work, we'll recognize some of these macros as being the extension points. Okay, so in portable.h, we're including deprecated definitions. Each FreeRTOS port has a unique port macro.h file. Originally, there's some preprocessor definition stuff that was used before. I guess we're not using that now. That's fine. And we've got port byte alignment. This is presumably byte alignment. So we could have a 32. I'm guessing I'm not sure if these are bytes or bits, but 32, 16, 8, standard powers of 2. I'm guessing these are just alignments that are different on various chips. MPU wrappers, I'm not sure what MPU is. See if we can find out. Memory protection. Okay, so the MPU is the memory protection unit. It's part of the CPU, and I vaguely remember learning about this in operating systems. But I don't recall off the top of my head what it's up to. But at any point, from our perspective, it's just a per chipset thing that's going to vary from chipset to chipset. And so as they're coding this operating system, they need to allow that to vary in some manner. Has Stack Overflow checking. So at least the common like desktop chips should have some way to prevent stack overflows. The smaller like hobbyist chips, maybe not, but this is one of the things you can set. You can set the architecture name. Some stuff about C++, and maybe that's just whether it's supported. I'm not sure. And then we get some logic in the form of macros. For example, this is going to set up the stack of a new task so it is ready to be placed under the scheduler control. So it's an operating system. We're going to have some scheduler. It's going to schedule tasks. The processor is going to have registers. The registers have to be placed on the stack in the order that the port expects to find them. Okay, so the port, if I'm understanding this correctly, is going to be the per processor or per chipset stuff, and they have different conventions about how you're going to put stuff into the registers. And I guess it has something to do with whether you're using MPU wrappers, etc. And you get different, it looks like, implementations of stack initialization. And then we have stuff for configuring the heap. We have heap stats, which I'm going to guess is heap statistics, which used to pass information about the heap out of vport get heap stats. And then heap region is used to define the start address and size of each memory region that together comprise the total FreeRTOS heap space. Sounds good. More heap region stuff. Map to memory management routines. So we're going to have some allocators, and those are, I guess, configured here. We have like free initialized blocks, etc. And then some stuff about configuring it looks like starting and stopping the scheduler. Set up the hardware ready for the scheduler to take control. This generally sets up a tick interrupt and sets timers for the correct tick frequency. Okay, and so on. Okay, so that's what the API looks like in broad strokes. Let's pick one of these. I was going to pick GCC. Maybe we will. I guess let's take a quick look at GCC, and then we get a bunch of different stuff like ARM. I'm not familiar enough, I think, with the ARM. I guess let's pick one basically at random. This was updated 3 months ago. And we have port.c. And we're just including some standard lib stuff, FreeRTOS.h for scheduler stuff, and task.h. And we're going to have a bunch of macros. So for example, we can look at the symbol list. And let's look at start scheduler. And we've got kind of inscrutable abbreviations like ULAPSR. I'm not sure what that is, but the meaning of this semantically is that there are 8 bits per byte, I guess. We're setting some volatile stuff, original priority, first user priority register. This, I'm guessing it's just, we're starting the scheduler. So this looks like fairly low level stuff, like setting up just the bootstrapping priority stuff. And then here we determine how many priority bits are implemented in the GIC. Okay. And here's some bit shifting, shift to the least significant bits. And presumably this is doing a bunch of stuff with registers. Let's see how many. So we have 45 occurrences of the word register. Am I matching them all? Yeah, I'm matching them all. So this, consistent with my theory, this is all stuff that's talking, I guess, directly to the chip. These look like assembly directives. And this is the entry point. And so that's really all I want to get out of this, I think. So with that in mind, here's what the actual API of FreeRTOS is looking like once you have a port that you're working with, that you're happy with. And we have a bunch of different headers, things that we can guess what they refer to. Atomic is likely atomic operations, like maybe atomic test and set. C routines, I'm going to guess, is coroutines.h. Stack macros are presumably macros for working with the stack. Event groups are going to be groups of events. I'm not sure if event has this particular. I don't know if these are like core to how RTOS works, but we're going to look at events in a little bit for sure. We have message buffers, the memory protection, some memory protection unit stuff, new lib, pico libc. I'm guessing this is a small libc implementation. Portable.h, which we looked at already. Project definitions, a queue semaphore, which we should open up. Stack macros.h, which is, how is this different from capital stack macros.h? I'm not sure. Stream buffer task.h and timer.h. I think I've opened up the C files for a lot of the stuff like tasks and timers and queues. I guess I might as well open up the list timer. I don't see, actually, yes, I do. Let's take a look at timer first. I'm going to guess timer is the first thing we need to understand. And we're getting code comments. I'm wondering if it's going to give us an overview of timers. These are IDs, type by which software timers are referenced. For example, a call xtimer creates a timer handle t variable. Okay. This creates a new timer, software timer instance. Is this going to tell us about, what I want to do is I want to learn about ticks. And that seems to be maybe be in this comment. Let's take a look at this comment here, this big one. It says it's for, I guess, pended function t. Okay. Oh, no. This comment's going to govern the thing below it, right? Which seems to be some macro around x timer create. So the thing that's creating the timer. Okay. So it's going to take a name, a timer period in ticks, and whether to auto reload. It's some whatever PV timer ID is, some identifier, I guess, that's distinct from its name, and a callback function. And oh wait, I changed my search to, yeah, okay. Let's take a look at this paragraph first. So you're going to give it the timer period in ticks, which is the ticker period. The time is defined in tick periods. So the constant port tick period ms can be used to convert a time that has been specified in milliseconds. For example, the timer must expire after 100 ticks. Sorry, if the timer must expire after 100 ticks, then x timer period in ticks should be set to 100. Alternatively, if the timer must expire after 500 milliseconds, then x period can be set to 500 divided by port tick period milliseconds, provided that config tick rate hertz is less than or equal to 1000. The timer period must be greater than 0. So that's a lot to, these are kind of like a lot of caveats to remember. The division may have some bad properties. I don't know if ticks are expressed in integers, but I'm guessing this is basically integer division. And so what I really wanted to get out is that, as far as I understand, we're thinking of time as something that ticks by, and we're scheduling things by ticks as opposed to, for example, frequency or clock time. And that's a big part of how how at least this real-time operating system operates. I think this is a general thing for real-time operating systems. And that's different enough from how we typically think about time in computers that I think it's worth looking at for a second. So for example, Stack Overflow. I want to understand what is meant by an operating system tick time and what's the use of it. The system tick time is the time unit that OS timers and delays are based on. The system tick is a scheduling event, i.e. it causes the scheduler to run and may cause a context switch. For example, if a timer has expired or a task delay completed. If the RTOS supports round-robin / time slice scheduling of tasks of the same priority, the OS tick may cause a context switch directly without the task requesting a delay or timer event. And a time, this is useful, an RTOS system tick period will typically be on the order of 1 to 100 milliseconds, but maybe longer. And so, in theory, if you have an operating system that's doing something like, let's say, helping you fly a plane, or it's like running some life support device in a hospital, you want to be able to guarantee that, that the function that is making sure that the heart is beating is running at regular intervals. And the way that they do that is through thinking about ticks as opposed to whatever the frequency of the chip is. Nearly every RTOS is equipped with a time source, generally provided by a hardware timer that interrupts the CPU at a certain rate, called the tick rate, which is generally chosen to be between 10 and 1,000 hertz. Okay, so that's ticks. Maybe just for fun, let's ask Bard. I'll say, tell me about RTOS ticks and how they're different from thinking about things in terms of, let's say, clock time, or maybe just time elapsed. They're a fundamental concept, the basic unit of time, blah, blah, blah. So RTOS ticks frequency, they occur at a fixed rate. So they will map onto some frequency, as you would expect. Resolution, they provide a coarse measure of time. While the frequency determines the maximum resolution, actual execution may not be perfectly aligned. They are primarily used for task scheduling, timeouts, and timekeeping. Real-world time flows continuously, not discrete, like RTOS ticks, etc. So I'll ask how about the general purpose OSs like Linux and Windows. Think in terms of ticks, like RTOSs. So while Linux and Windows share some similarity with RTOS in their use of timers and scheduling, they don't directly operate on the concepts of ticks in the same way. Here's a breakdown. So ticks have fixed frequency and direct timekeeping. RTOS ticks directly correlate with the passage of time within the system. And in Linux, in Windows, we have variable timekeeping. They rely on high-resolution timers and interrupts. This allows them to achieve finer granularity and adapt variable loads and demands. Indirect timekeeping in these systems is not directly tied to a fixed frequency like RTOS ticks. Instead, it relies on various mechanisms and scheduler granularity. When RTOS tasks are typically scheduled based on ticks, Linux and Windows, while they are blah, 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 Linux and Windows use a more flexible approach. They consider various factors, including priorities, deadlines, etc. Okay, so that's I think the maybe one big, possibly the big conceptual difference between real-time OSs and regular OSs. But now that we have these timer ticks, we can kind of intuit at least how scheduling and other things will work. And we'll see that going on. All right, so still within timer.h. Let's see. So creating a new timer. This is, I'm guessing, not the main timer. This is maybe for creating general timers. So software timers use a block of memory in which the timer data structure is used. If a software timer is created using xtimer_create, then the required memory is automatically, dynamically allocated inside the xtimer_create function. If a software timer is created using xtimer_create_static, then the application writer must provide the memory that will be used by the software timer. Okay. They are created in a dormant state, and you have to call API functions to activate them. I guess essentially timer.start or whatever. And then you give it a name, etc. The PX timer buffer looks like it's for the static timers. So you essentially give it some chunk of memory. All right, what else can we do? We can get timer.id, setters and getters, etc. It's essentially for the timer struct. That's not so fascinating. We have xtimer daemon task handle, which is going to return a task handle type. and takes no arguments. Simply returns the handle. Okay, this is the handle. I thought it was going to handle some daemon task. What it really is returning the handle by which you can talk to the task. And then you have a timer start function, which when you call it is going to, I guess, call this timer generic command with some ticks to wait that seems to not be set by the caller. Maybe that's part of the port. And that you're setting some command start. So X timer generic command seems to be basically like a it's like the command pattern. You're going to give it commands, and it's going to kind of do dispatch as if it was like an RPC server. And then you can stop the timer. And that's all nice. You can change the period. How would you change the period? I'm not sure. It gives you an example usage. The function assumes X timer has already been created. If the timer referenced by X timer is already active when it is called, then the timer is deleted. If the timer referenced by X timer is not active when it is called, then the period of the timer is set to 500 milliseconds and the timer is started. So this is okay. So this is describing this particular usage in code. So this is checking if it's active, etc. So this is not something. This is not. I thought originally that this was the contract of the current function, but this is not part of the contract. It's something you have to program if you want this behavior. But this is just showing a call. But what does it do? Timer functionality is provided by a timer service / daemon task. Many of the public FreeRTOS timer API functions send commands to the timer service task through a queue called the timer command queue. And I'm guessing that this is essentially what X timer generic command does. There's some timer command queue, and we'll see the queue implementation in a few minutes. And you're going to essentially queue up commands for the timer, presumably. It seems to be what this is saying. The timer command queue is private to the kernel itself and is not directly accessible to application code, which makes sense. It'd be kind of messed up if your application code could change the behavior of the real-time OS. And then the length of the timer command queue is set by, you can configure it. Change period changes the period of a timer that was previously created. And I'm guessing that it just like changes the number of ticks to wait for. They're specified in tick periods. So the constant port tick period ms can be used to convert a time, etc. So you can convert between milliseconds and ticks. Okay. So I'm not seeing anything else super fascinating in timers. So let's move along. Here's timers.c. This is the implementation. And I'm guessing that part of this is just going to be essentially bottoming out at the port stuff. So some of the timer stuff is presumably going to be tied to how whatever oscillators or clocks work in the chip. But we might be able to see some stuff about queues. We have some configuration stuff like no delay, max time before overflow. Service task core affinity. So this is, I guess, for chips that have multiple cores. And affinity is presumably going to govern whether similar tasks or related tasks or the same task are scheduled on the same core over time. And you can say no task affinity. So like, if something like task 1 has been running on core 1 for a long time, but then core 1 is suddenly busy. If you have no affinity, presumably it's going to say, well, we can run it on core 2. But if you have affinity, maybe it'll try harder to run it on core 1. And we have a struct, a timer control struct, which has what? We've got some, let me kill this window for a second. And I'm pretty sure I don't need this window at all. Does this shrink? Yeah. Okay, so we've got a name, some linked list. Whoops, what is it doing? I'm not sure. And where to go? No. So there's a standard linked list item used by all kernel features for event management. Okay, so this is some They use linked lists for event management. And you've got a period and ticks, an ID, a callback, standard sort of stuff you would expect from a struct that's handling timer stuff, given everything else we've seen. There's some parameters like tick type. I'm not sure what the different types are. I see what tick type is. Not sure. Maybe we'll see that later. Okay. We have a list of active timers. We have a list of current timers and an overflow list. What does the overflow list do? The list of which active timers are stored. They reference an expired time order. So what's going to expire first? Only the timer service task is allowed to access these lists. Okay. I'm not sure what overflow is, but something is overflowing. I don't know if the time is overflowing or something else. And then we have a queue to send commands to the timer service task. And send commands to the timer service task. So I think that's the queue that we were seeing in the header. And we've got the timer queue and the task handle, which is presumably a handle, like a way that you can get a reference to the handle for the task. Okay. And then all of this stuff looks like relatively standard, kind of as you would expect it to be, given the setup. So here's tasks, and maybe we should look at the header first. This was trying to figure out what's up with tick type, but I don't think we have the definition. All right, whatever. Do we have task.h? Yeah, let's look at task.h. Whatever inc is, inc task.h. If task kernel version ends with 1. Okay, so this is some version stuff, some MPU region stuff. I would like to just kind of see a struct, what they think of, how they're thinking of a task. We have an enum. These are like the states that the task can be in. You can be running, ready, blocked, suspended, deleted, or invalid. That all makes sense. Blocked. If you're blocked, I'm not sure if you have a reference to who is blocking you. Suspended means what? That the task being created is in a suspended state or is blocked with an infinite timeout. Okay. And then we have another enum. These are actions that can be performed when vtask notify is called. You can set bits in the task's notification value. I'm not sure what that means. I guess each task has some sort of notification value that is presumably like a bit flag, and you can set some of the bits. You can increment the task's notification value. Maybe notification value is used possibly for some sort of, is somehow used in the priority algorithm. And you can set value with overwrite. This is setting it to a specific value, I guess, as opposed to just setting individual bits, even if the previous value has not been read versus only if the value has been read, right? Something like that. Yeah, okay. Then we have some timeout stuff, including the overflow count. Maybe overflow is like, once you've timed out, overflow is possibly the amount of time that's gone on since you ran out. Not sure. And we have some memory range stuff associated with the task. Parameters required to create an MPU protected task. This has things like the task function. There's some task function type, which we haven't seen yet. A name, some stack depth stuff, parameters. Oops, no. There, let's see if we can find some task struct. Go over to the symbol panel. Get rid of this search. We saw task state, we saw e-notify action. Task status, did we see that? This is used with the task get system state function to return a state of each task in the system. So task status has a handle. Everything has a task handle, the task name, task number, the current state, which is the thing we saw before, whether it's running, suspended, etc. Its current priority, which is a U base type. I'm not sure if we've seen that base type yet. A base priority, which is the priority to which the task will return if the task's current priority has been inherited to avoid unbounded priority inversion when obtaining a mutex. So this is some sort of inherited priority, and they're worried about priority inversion. And I'm guessing that tasks have parent tasks, and that's what that's about. A runtime counter, which is, I guess, the total runtime allocated to the task so far, as defined by the runtime stats clock. Allocated, I guess, I'm thinking this means the time that it's actually run as opposed to the time that's been set aside to run, but I'm not positive. And then the lowest address of the task stack area. So we still haven't seen the task struct, I think, yet, but we can infer that it has some sort of reference to its stack. It has a name, some priority, and some function to run, possibly some arguments to pass to that function. And then the high watermark, which is the minimum amount of stack space that has remained for the task since the task was created. So the stack is going to grow, and then the high watermark is, I guess, the largest it's been so far. Okay. But where is the actual struct? You see some stuff about task affinity, task status, task create, task delete, task delay, and getters and setters for various parts of the tasks. We have task list tasks. What is this? I'm not sure. This function, blah, blah, blah. I don't know what that does. It's going to do something about listing tasks. So let's just choose one of these, like task delete, and this should tell us. I'm going to take a task handle. Let's see if we can find task create. We have X task create and V task create. I don't know how X and V differ. Let's look at X task create first. The task creation API. Create a new task and add it to the list of tasks that are ready to run. You're going to give it a task code, a name, some stack depth parameters, which is a void star, so it can be anything. The priority and a task handle. I'm guessing the task handle is possibly an out parameter. So the UX priority is the priority at which the task could run. Systems that include MPU support can optionally create tasks in a privileged system mode by setting the privilege bit. And then the created task is used to pass back the handle by which the created task can be referenced. So that is, this is an out parameter. Okay. So the task handle is maybe the type that I'm looking for. So there's a couple of, it looks like there's different implementations depending on whether dynamic allocation is supported. I go here, I dig into the actual implementation. Should be able to. Did we only have V task create? Sorry, did we only have X task create? Okay, so the V task, whatever X and V are, I thought for a moment that we only saw that we saw both, but the truth is we only see one. So we can probably just jump to task handle, right? Task handle.t_t. Will it jump to the definition? Come on, what you call it? Let's just try doing a search in the whole thing. What? That's what I meant to do. Do we see lots of references to it? Do we see an actual definition of the struct? Or like a type definition? We're defining X task handle to be task handle. Maybe it's in the FreeRTOS dot. Let's try doing struct X task handle T. Sorry, struct task handle T. But Emacs. I think I misspelled it. If we just, okay, so that's the tags file. Just grab one of these that has and jump to definition. There we go. Wait, what? Oh, okay. So there's a task control block that I'm looking for. Here we go. All right, so the task control block has a stack type, some MPU stuff, a core affinity mask, so some mask used for specifying affinity, a list state list item. The list that the state list item of a task is reference from denotes the state of the task. So this is the whether you're ready, blocked, suspended. Use this thing that's used to reference the task from an event list. I guess these are different ways of referencing the task. We have the priority, the stack, the start of the stack, which we inferred must be part of the task struct. The name, which we also suspected was part of the task struct. The end of stack, and whether to disable preemption. Critical nesting holds the critical section nesting depth for ports that do not maintain their own count in the port layer. So this is used for nesting. I don't know if that's nesting in the sense of recursion, but how nested can the critical section get? And then some TCV stuff, some task number, more priority stuff. And these are kind of these are behind ifs. So if we're using mutexes, then we have some mutex stuff. If we're using application task tag, then we have some of that stuff, and so on. And then some stuff about notifications. And I think this is where it was. And some stuff about delay and possibly an error number, I guess, if the task failed. Okay, so that's what the task struct looks like. That's all reasonable. Okay, let's move along. So here we are at include, which I think I already kind of went through all. I already picked out the stuff that I wanted from here. Then here's the tasks.c implementation. I'm going to guess this is not going to be especially informative, given the stuff that we already know. We're going to get getters and setters for all of the all of the things that we've seen, like in the struct. We're going to get getters and setters for things like priority. I doubt we have any scheduling logic here. I mean, there's entry points that we can set things that the scheduler will care about, but I don't think this will tell us about how scheduling is done, for example. Here's Q.C, which is going to be the implementation of Q stuff. We have a header somewhere, I think, maybe. That's okay. I don't have the header open, but maybe I don't need it. And what do we have? Things like whether the queue is locked or unlocked. The queue type, which is set to PC head. When the Qt structure is used to represent a base queue, its PC head and PC tail numbers are used as pointers to the queue storage area. So since we have a head and tail, this is presumably just a linked list. When the Qt structure is used to represent a mutex PC head and PC tail pointers are not necessary. And the PC head pointer is set to null to indicate that the structure instead holds a pointer to the mutex holder, if any. Okay. Map alternative names to the PC head and structure member to ensure the readability of the code is maintained. All right, so we have this Q pointers thing, which has a reference to the tail, a byte at the end of the Q storage area. And then we also have a PC read from or read from. The last place that the queued item was read from when the structure is used as a queue. Okay. They don't believe in short lines, I guess. So a lot of these comments kind of run off to the side. Then we have semaphore data. We'll see semaphore in a second, but it's got a reference to the mutex holder, which is a task handle, the handle of the task that holds the mutex. Okay. And the recursive call count maintains the count of the number of times a recursive mutex has been what? Has been recursively taken when the structure is used as a mutex. Okay, so we're going to maintain how many times I guess people try to take the semaphore. Semaphores do not actually store or copy data, so have an item size of 0. Okay. And then here's the queue definition. This is the structure, I guess. The old naming convention is used to prevent breaking kernel-aware debuggers. Okay, and so I'm guessing definition is maybe what it means with the old naming convention, because maybe you would otherwise just call this the queue struct. But we have the head, a reference to the head, the place to write to, the free space in the storage area. And then we have either an XQ or a semaphore, which I think we saw some of above in the same file. A list of tasks waiting to send, a list of tasks waiting to receive, and that are blocked waiting to post into this queue. Okay, so waiting to send are things that are trying to write to the queue, to this particular queue. Waiting to receive are tasks waiting to read from this queue. Messages waiting is the number of items in the queue. The length of the queue defined as the number of items it will hold, not the number of bytes. That I'm guessing if we scroll over there, it's saying that message waiting is the actual size of the messages in the queue. Length is the maximum possible size. And then item size is the size of each item that the queue will hold. And then we have these two lock things. One stores the number of items received from the queue, and the other stores the number of items transmitted to the queue. So I guess these are like counters, maybe used for statistics or possibly for optimization. And what else? Okay, so that's basically it. So we're going to have the standard queue operations as well. Like, for example, peak. Let's look at peak. So to do xq peak, you're going to give it the queue itself, the handle to the queue, a buffer, possibly to write stuff into, and the number of ticks to wait. And we set entry time set to false. And we, I guess, get ready to create a timeout. PC original read position is maybe that's for restoring to the original position if something fails. And we take a constant reference to the queue. Then we call trace enter queue peak with the same inputs. I'm going to guess trace enter is a version of this that is going to be traceable. So you can do possibly auditing. And then check that the pointer is non-null using an assert. Check something about the buffer. Essentially that is non-null, has the appropriate size. We check if the scheduler is suspended. So we do that by getting the scheduler state for the task. I think, I'm not sure if there's like a per task scheduler. And we look at whether we're using timers, in which case we do an assert that checks the scheduler. And then we have this infinite loop. We're going to call task enter critical. So I guess this is the critical the critical section of the task. And we're going to look at the number of messages waiting, or rather, yeah, that's the number of messages, right? We check that it's bigger than 0, so that we have at least one message. And we move to the position. Remember the read position so it can be reset after the data is read from the queue, which is what my speculation was of what that variable is for. Then we're going to copy data from the queue using this private copy data from queue function into the buffer. And then we're going to call trace queue peak again. Is that the same thing we called before? We call trace enter x queue peak, and now this is trace queue peak. How's that different? I'm going to guess that enter says we're about to start tracing possibly, and then maybe trace queue peak is the thing that we call inside the critical section. And we're not removing the data, so it's reset. Okay, so since we're just peaking, we're not taking something off of the queue. We're going to return essentially the read head to where it was before. And then we are checking now since there's still data in the queue, we see if there are any other tasks waiting for the data. This is just some standard list to check if there's data. And then we call task exit critical to indicate that we've left the critical section. And we call trace return queue peak. I guess that's the final call to whatever this tracing logic is that is tracing peak stuff. And then we have this else. What was the if statement? Okay, so if there's data on the queue, then we do that. If there's not data on the queue, then we wait for some number of ticks. And there's possibly timeout, etc. But I'm happy covering just the happy case. Let's see if we can find this trace stuff. It comes from the FreeRTOS header. So let's take a look at the FreeRTOS header maybe as the next thing. So this is if deft. So I guess maybe this is maybe this trace is something that you can set if you need to debug or trace whatever's going on. And is this an implementation? I don't know. Is 1880 where I just was? Yeah, I'm not sure how to tell GitHub that I want to go to the definition. But at any rate, let's go back to the FreeRTOS header and take a look at this. Since this seems to contain some basic stuff. All right, a bunch of kind of like bookkeeping stuff. We have acceptable values for config tip width in bits. So they can be 16-bit. A tick width can be 16, 32, or 64 bits. And this is more stuff about configuring the tick width, some stuff for importing defs, maybe project definitions, configuring stack size, etc. lots of configuration stuff that might differ, depending on what your application is, possibly differ depending on the chip. Although most of that stuff I would suspect it should be mainly be in the ports directory. Config precondition should be defined as config assert. The CBMC proofs need a way to track assumptions and assertions. The config precondition statement should express an implicit invariant or assumption made. Okay, so this is some way of specifying what your assumptions are. And I don't know if CBMC proofs are something that happen in at runtime, or if that's something built in, or if there's an external model checker. So CBMC is a bounded model checker for C and C++ programs. It verifies memory safety, which includes array bounds checks and checks for the safe use of pointers. So this is basically static analysis from Carnegie Mellon. And there's support for it in FreeRTOS, which makes sense because our real-time operating systems are often used for things where safety or performance is critical. So you want to make sure that you're not doing things like having memory leaks or use after free stuff. Then we have this trace start used to perform any necessary initialization. For example, open a file into which the trace is being written into. Okay, so you're going to there's some functionality for trace that's going to essentially, as you're running, write down an execution trace so that you can look at it, debug it, run analysis on it. Priority disinherit presumably is going to disinherit a child's priority from its parent. Called when a task releases a mutex, the holding of which has resulted in the task inheriting the priority of a higher priority task. Okay. I guess this is when maybe a low priority task holds a mutex, but the higher priority task needs the mutex. So this mutex px TCB of mutex holder is a pointer to the TCB of the task that is releasing the mutex. UX original priority is the task configured base priority. Okay. So I think that's related to priority inversion. I'm going to try this lava thing. It's billed as a thing for vision, but it's one of the LLMs that I think you can run locally. So I'll see just to see how it does. Tell me about priority inversion. High traffic. All right, well, it's a free demo, so I don't think that reflects on the model. Let's ask ChatGPT. It's a phenomenon in real-time systems and concurrent programming where a low-priority task holds a resource needed by a high-priority task, preventing the high-priority task from making progress. The situation can lead to unexpected and undesirable consequences in the system's performance and behavior. So are there known examples of critical systems, I'll say of deployed critical systems failing due to, let's say failing catastrophically due to priority inversion? So it says the Mars Pathfinder mission in 1997. The mission included the Sojourner rover, and a bug in the mission's software caused a priority inversion problem. The issue led to delays in the rover's responses to commands and data collection, affecting the mission's overall success. While it did not result in catastrophic failure, it underscores the importance of priority inversion in critical systems. Okay. All right, so back to FreeRTOS.h. A bunch of trace event stuff, which I'm just going to kind of blow on past. Like all trace events all the way down. I thought we ran into like a bunch of like structs and stuff that were defined here. Okay, now we're past the task stuff. We have stuff about configuring post-sleeping processes. configuring whether to use Q sets, some callback stuff. Config max, config printf. Something about configuring printf and whatever at max what, I'm not sure. Min. Okay, so this is just some defining the max function. I don't know why it's called config max and config min, but it's just a standard like define for max and min. The application writer has not provided their own max macro, so define the following generic implementation. Okay, so I guess they're calling it config because it's generic or something like that. If we're enabling backward compatibility, we define a bunch of stuff that is presumably from the old times. This is a huge thing that's I'm going to mostly ignore. That seems to be about dynamic allocation. Some list data structure stuff. X static TCB. In line with software engineering best practices, especially when supplying a library that is likely to change in future versions. FreeRTOS implements a strict data hiding policy. This means the task structure used internally by FreeRTOS is not accessible to application code. However, if the application writer wants to statically allocate memory required to create a task, then the size of the task object needs to be known. Okay, and some more stuff about that. So more stuff about data hiding and the queue and the event group and the timer. Okay. You usually don't see so many sermons about best software practices, but I guess what they're saying is that they want to hide the underlying implementation in some way. That's standard. It's common to have a public struct and an internal struct that you can modify more rapidly or whatever. Here's event groups. I think I have the event groups header. I'm not sure I do, but let's go back to header land and look at the headers, because what I'm noticing so far is that the implementations are pretty noisy, and that maybe the headers might be the easiest way to get a grasp on what's going on with some of these basic data types. So event groups we want to look at. Let's do that now. All right, these are presumably groups of events. What does that mean? I'm not sure. We've got some bit fields, control information, and a task event list. So I guess each task has an event list, or at least a task can have an event list. Maybe it's not mandatory. And we have things like clear events on exit, unblocked due to bit set, wait for all bits. These are different defines based on whether your tick width is 1632 or 64. But these all seem to be the same events, just defined with different kind of magical numbers. An event group, here we go, is a collection of bits to which an application can assign a meaning. An event group. Okay, so it's a collection of bits. And I guess FreeRTOS just thinks of them as bits, but your application can give them some sort of semantic meaning. For example, an application can create an event group to convey the status of various CAN bus related events, in which bit 0 might mean a CAN message has been received and is ready for processing. So CAN bus I recognize as being something that's used in the automotive industry. I don't know if it's strictly speaking only automotive. CAN bus, the controller area network bus, is a vehicle bus, which is different from a bus which is different from a vehicle that is a bus. A vehicle bus standard designed to allow microcontrollers and devices to communicate with each other's applications without a host computer. Okay, so microcontrollers, okay, so development of the CAN bus started in 1983. So where are we in 1983? Let's see. Just to pull up an image of a 1983 vehicle. This is what things were looking like in the 1980s. about 1980 truck. This was before, I guess, we had general purpose computers in cars. So let's take a look at what computer, like personal computers were looking like. They look kind of like this, gigantic. So this was from this is at least originally from an era where the you didn't have a general purpose computer, you had a bunch of microprocessors. So we want, or rather microcontrollers. So we want the microcontrollers to be able to talk and communicate to each other in kind of a distributed fashion without needing to talk to some cloud or mainframe or whatever you want to call it. There's not some larger computer that's going to coordinate their activity. And so they are presumably going to do stuff like gossiping to each other. And it's a favorite thing for people to attack. So if you do like CAN bus, black hat or something, then there seem to be lots of CAN bus, a beginner's guide, hacking my roommate's car, lots of stuff. So this is the CAN bus. And then vehicle bus is presumably just the generic example of the bus used in a vehicle. And nowadays we have essentially like tablet computers for the for like the entertainment system. And I'm not sure how many other general purpose computers there are in cars these days, but I would imagine it's a fair number. Okay, so this is just an example. You can use it with the CAN bus. Bit 1 might mean the application has queued a message that is ready for sending into the CAN network. And bit 2 might mean it is time to send sync message onto the CAN network, etc. So you're giving this stuff meaning, but you're not. This is maybe somewhat similar to how like protocol buffers work. So when you write a protocol buffers file, the thing that it compiles down to is ultimately over the wire, it's going to send the thing on the wire doesn't know what your method names are called or what your the messages are called or what the semantic meaning of anything is, as opposed to like JSON. When you're sending JSON strings, if a person were kind of intercepting that string, they would be able to see that title of book is A Tale of Two Cities or whatever. In this setup and in the like protobuf setup, it's the application that is in charge of knowing what the semantic meaning of the bits is. And this is just kind of using like an integer, a collection of bits as a message type. And then the application logic is going to interpret those messages differently depending on how you programmed it. A task can then test the bit values to see which events are active and optionally enter the blocked state to wait for a specified bit or a group of specified bits to be active. To continue the CAN bus example, a CAN controller task can enter the blocked state and therefore not consume any processing time until either bit 0, bit 1, or bit 2 are active, at which time the bit that was actually active would inform the task which action it had to take. The event group's implementation contains intelligence to avoid race conditions that would otherwise occur were an application to use a simple variable for the same purposes. This is particularly important with respect to when a bit within an event group is to be cleared. So this is, to continue with the like protobufs analogy, this is kind of saying that like there's some work going on to make sure that the passaging of messages is sane and not that all the hard things that you have to figure out, that things that race conditions that might happen like 1 in 1,000 times, etc. Those are all worked out in the event group's implementation, so that you as the library author just have to focus on assigning meaning to the bits, and you don't have to worry about the finer points of real-time operating systems. Okay, so we're in just the header, right? Oh, no. I feel like when I intentionally click on something in this interface, it rarely takes me where I want to go or like shows me the definition I want to see. But when I accidentally click, it frequently loses my place. Okay, So what can we do? We can get the bits from the group, and we can set the bits from the group somewhere. This is event group get bits from ISR. What is ISR? Something, I'm not sure. You can delete. This is just kind of like getters, setters, and deletes. And then somewhere I have the C implementation. Yeah, here's the implementation file, event groups.c. And I'm going to guess an event group is just like an int of some sort. Although maybe that's not. Here's the type, event group type. We've got event bits, which is going to be the thing that's the actual bits. We've got a list of tasks waiting to see. Possibly, if we're doing tracing, I guess, then they've got a group number and some stuff about whether it's statically allocated. We get to see the event bits type. None of these seem to be about define events. Was it events underscore groups? No, event bits, I think. Let's just set the tick type. The type that holds event bits always matches tick type D. Therefore, the number of bits it holds is set by config tick type width in bits. Okay, so 16 bits, 32 bits, etc. All right, here's list.h, which is presumably just going to be a linked list implementation. We saw a queue, which was basically a linked list, and I'm not sure how this is going to be different. It's probably not too different, but maybe less focused on the queue API. The list structure members are modified from within interrupts. Okay, and therefore, by rights, should be declared volatile. Yeah, however, they are only modified in a functionally atomic way within critical sections with the scheduler suspended, and are either passed by reference into the function or indexed via a volatile variable. Therefore, in all use cases tested so far, the volatile qualifier can be omitted in order to provide moderate performance improvement without adversely affecting functional behavior. Okay, so this is maybe something, if you have something super critical, like life and death critical, you may want to double check that this is always behaving the way you expect it to. Okay, so we've got some macros that can be used to place known values within the list structures. Things like list first, list item, integrity check value, first list item, integrity check value, etc. I'll ignore most of those. Definition of the only type of object that a list can contain. So we've got this struct xlist thing and an xlist item. And I'm not sure what this integrity value thing is. Integrity check value. I'm not sure if this is a command to check the integrity of something or if this is used in integrity checks. We've got a x item value, which seems to be of tick type. So I guess essentially a word that's 16 bits or 32 bits or something. The next and the previous, so we have a pointer to the next a pointer to the previous. These seem to be volatile. The item value is also volatile. In owner, which is a pointer to the object, normally a TCB that contains the list item. There is therefore a two-way link between the object containing the list item and the list item itself. So the object points to the list item points to the owner, to the object. In a container, this is a pointer, I guess, to the list in which this list item is placed, if any. So that's essentially just a pointer to the head, if I am understanding correctly. And then a second integrity thing, set to a known value if blah, blah, blah. Okay, so I guess by integrity means you're going to set these to known values, and then you can check for those values in your code. And if something like overwrote a block of memory, then you could find out where that corruption happened in the list by looking for the place where the first value was valid, but the second value was invalid. And then you would know, I guess, that somehow in between those two, the corruption took place. I guess is that the idea? That might be the idea. All right, here's the definition of the type of queue used by the scheduler. So we've got this list T thing with the integrity values. It's got the number of items. An index, which is used to walk through the list. I guess this is essentially a pointer to the last item returned by a call to get owner of next entry. So essentially a cursor into the list, and then the list end. And this is what's used by the scheduler, apparently. And some macros that look like they're getting and possibly setting stuff. List item value, access macro to set the value of the list item. Okay, so this is a macro that just takes the list item and the value and just gets the value and sets it to the thing you pass it to. You can get the head entry, get the current list length, you can get the owner of the next entry, and it's got a huge comment to obtain the owner of the next entry in the list. This index is used to walk through the list. Calling this get owner of next entry increments the index to the next item in the list and returns that entry's owner. Using multiple calls to this function is therefore possible to move through every item contained in the list. I guess that's common enough that you would want to do that. And you can insert things at the end. This is all. The rest of this seems like standard list stuff. So we have a little bit of interesting structure, but otherwise mostly a standard list. Here's stream buffer. I'm going to guess I can ignore stream buffer because we haven't seen much about them. Let's see. Some MPU stuff about callbacks. This is the implementation. Can I find a stream buffer.c? Here's a coroutine implementation. Here's semaphore, which I think is more important. Let's maybe move stream buffer to the end and see if we can go back to the includes directory. Pull out coroutine.h. Maybe stream buffer. And have we missed anything scheduly? I'm not sure. Did we look at atomic.h? I don't think we did. Move some of these to the front. Okay, so here's semaphore. This should just be essentially just a semaphore. Go yeah, so semaphores. Thank you, Wikipedia. Semaphores are flag communications originally, and apparently they go back at least to ancient Greek, presumably earlier. The idea here is that you have line of sight communication, right? So you have instead of sending a messenger like in a boat, this is communication at the speed of light before we had anything like computers. So that's good. But I wanted the programming semaphore. A variable or abstract data type used to control access to a common resource by multiple threads and avoid critical section problems in a concurrent system. They are a type of synchronization primitive. Library analogy. Yeah. What I want to know is, I want to be reminded of how they are different from other synchronization primitives. And maybe the way to do that is let's ask Bard. Okay, so succinctly, how do semaphores differ from other communication primitives? I'll call them synchronization primitives, like mutexes. So mutex, as a locking mechanism ensures that only one thread can access a shared resource at a time, and semaphores are a signaling mechanism. They track the available slots for accessing a shared resource, allows multiple threads access but limited by the number of slots. The mutex is 0 to 1. A semaphore is 0 to n. So is a mutex just a special case? A semaphore, the size 1. Yeah, okay. So a mutex is conceptually, not in its implementation, is just a semaphore with size 1. And then I'll ask what are some other synchronization primitives I should know about. So condition variables used in conjunction with mutexes to signal specific conditions within a critical section. This is used in Java, I think, a lot. Threads waiting on a condition variable are suspended until another thread signals it, allowing them to resume execution, useful for implementing synchronization patterns like barriers and producer-consumer queues. Events used to signal a specific event occurrence. Spin locks, similar to mutexes, but use busy waiting instead of blocking threads. Threads waiting on a spin lock continuously check if it's a variable, consuming CPU resources. Useful for short critical sections where blocking would be inefficient. Read-write locks allow concurrent access to shared resources while maintaining exclusive write access. Yeah, so these are for things where anyone can read, but only a few people can write. Monitors are higher level synchronization construct combining mutexes and condition variables. I forget exactly how monitors go. And then barriers. These are places where all the threads have to wait for each other. And semaphore slim. Sounds like that could be a cool nickname. Semaphore slim. Lightweight alternative to semaphores in the .NET environment. All right, cool. So semaphores. So these are kind of like locks with multiple slots. In many usage scenarios, it is faster and more memory efficient to use a direct to task notification in place of a binary semaphore. So there's some old stuff that's deprecated. The macro that implements semaphore by using existing queue mechanism. The queue length is 1, as this is a binary semaphore, which at least Bard is claiming is the same conceptually, like it has the same API, same expressiveness as a mutex. The data size is 0, as we don't want to actually store any data. We just want to know if the queue is empty or full. The type of semaphore can be used for pure synchronization between tasks or between an interrupt and a task. Semaphore need not be given back once obtained, so one task interrupt can continually give the semaphore while another continually takes it. For this reason, this type of semaphore does not use a priority inheritance mechanism. I'm not sure how that's, doesn't seem entirely semaphore-y, but I guess it is. You can create the binary semaphore. Do we only have binary semaphores? Yeah. So we can create them. What else can we do? More creations. There's like static versions and non-static versions. You can take the semaphore, which we'll call I guess X semaphore take is set to the queue version. And what else? That seems to be about it. If we can find anything about in their documentation about if they want to say anything more interesting about semaphores. I guess that's like, this is like the automatically generated documentation. Here's an example. In programming, a semaphore is a variable used to control access to a common shared resource that needs to be accessed by multiple threads or processes. It is similar to a mutex in that it can prevent other threads from accessing a shared mutex or critical section. However, where a mutex implies a level of ownership of the lock, that is, a single thread is said to have the lock while executing in a critical section, a semaphore is a counter that can allow multiple threads to enter a critical section. Yeah. So we've got in theory, it's just a shared counter that can be incremented and decremented atomically. However, in practice, you rarely use semaphores like this, as even the critical section, there's no way to protect individual resources with just one semaphore. You would need to use other protection mechanisms like queues or mutexes. Okay. I'm not sure what this is saying, but it's a semaphore. It's going to guard the critical section. Let me see what they are saying about binary semaphores again. Is this the first occurrence? For some reason, GitHub has stopped rendering. Okay, whatever. That's a cue to move on. Here's atomic.h. This is going to be atomic implementations, and I think that this is, since atomicity is probably mostly governed by the chip, I'm going to guess these are just going to call stuff that's in the ports directory. So for example, atomic compare and swap. Here's atomic compare and swap pointers. We're going to say that we've atomic entered critical, atomic exit critical, and then we're going to swap the pointers. Let's see if we can find a definition of enter and exit critical. Here we go. Ultimately, it seems to come down to port set interrupt mask from ISR. So I think that this is when you do port stuff, you're going to set this in a way so that when this macro is called, you're actually doing atomic things on the microcontroller, and then this file is basically just saying atomic enter critical, doing some stuff, and then calling exit critical, and that's straightforward enough that I think that we can just move on. Stream buffer, I'm going to guess, is not so important. Just going to be some buffer, right? Create a new stream buffer using dynamically allocated memory. The number of bytes in a stream, etc. You can delete it, check whether it's full, check the bytes available, and so on and so forth. Coroutines might be interesting. We have this handle T that's used to hide the implementation of the coroutine control block. The control block structure, however, has to be included in the header due to the macro implementation of the coroutine functionality. So here's the control block. And there's a coroutine function. Generic list item is the list item used to place the CRCB in ready and blocked queues. Coroutine control block must be CRCB. So this is for queuing up the coroutine. And then we have this event list that's used to place it in event lists, where the event list, I think, is the same as the event group, which is just essentially some message passing implementation. And the priority of the coroutine, the index used to distinguish between coroutines when multiple coroutines use the same coroutine function. Okay, and then state, which is used internally by the coroutine implementation. All right, and so you can create coroutines. This just from other headers, I'm going to guess this is largely getters and setters. In the header, now that we know what the struct is, let's see if we can find the coroutine.c implementation. So far, I feel like we haven't really seen scheduling. We've seen timers. Okay, so here's a coroutine implementation. We have the list of, I guess, coroutines that are ready, etc. Some initial state. You can add, this is a private function to add a coroutine to the ready queue. Place the coroutine presented by the input parameter into the appropriate ready queue for the priority. How is priority handled? I'm not sure. We check the priority and set this thing. And then we insert at the end of, I guess we have an array of, this is the ready coroutine list. And what we're taking the priority. I'm not sure with all of this stuff, but this seems to be the end of this index into the coroutines list. Somehow we're putting the coroutine control block into the ready list, indexed somehow by priority. I'm not sure with the syntax and all of the parentheses what lines up with what, but that's ultimately what we're doing. We have this utility to ready all the lists used by the scheduler. Then we have the pending ready list, coroutines that are readied by an interrupt cannot be placed directly onto the ready list. There is no mutual exclusion. We have no mutex, I guess, that guards the ready lists. And so when they're readied by an interrupt, they can't be placed directly. I don't know what readied by an interrupt is. Maybe that means that the interrupt, the function running in the interrupt wants to schedule them. Instead, they are placed in the pending ready list in order that they can later be moved to the ready list by the coroutine scheduler. So the coroutine scheduler is going to have this pending list, and it will decide to, I guess, periodically take things from the ready list and add them to the actual list. And then we have this macro that looks at the list of coroutines that are currently delayed to see if any require waking. Okay, so we have a list as things. So as state change, I guess they get moved around to different lists, and then the scheduler is going to walk over these lists at various points of time and see whether they need to wake up, whether they need to be rescheduled, etc. Then we have this coroutine create thing. Is this interesting? I'm not sure, but maybe we can see what list it goes on to first. If the PX current coroutine is null, then this is the first coroutine to be created, and the coroutine data structures need initializing. So you call this private initialized coroutine list thing. This just checks the priority within the lists. Fill out the coroutine control block. So we're just setting the things in the struct. Initialize all the other coroutine control block parameters, just more initialization. Set the coroutine control block as a link back to the, okay, this is just linking back. And then we're going to add it to the ready queue. And then whatever this is doing, setting PD pass to X return. PD pass came from where? I'm not sure. Maybe it was defined in all the initialization, but I guess that's the thing that's going to be returned. You can add it to the delayed list. You can give it some ticks to delay, and it will, I guess, periodically check that list. And once the number of ticks is processed, it will schedule it. We have the pending ready list, the private one, which I think we saw some stuff about. Here's a function to check the delayed list. We're going to get the past ticks by getting, I guess, the current tick count and subtracting the last tick count. And as long as this past ticks is non-zero, essentially positive, then we're going to increment the X coroutine tick count, decrement past ticks, and check whether we've overflowed. And while, I guess this will check for timeouts. And okay, so maybe I should actually look at this. Yeah, no, I don't. Oh. Okay, so this is checking if it's overflowed. this is, see if the stick has made a timeout. Okay, so this is, I think, what we want, right? So we check if the delayed coroutine is list contains something. This confused me for a second because it looked like we were checking whether it's empty, but we're checking whether empty is false, which means it's populated. It's a double negative thing. Then we get the owner of the head entry, which is the first thing on the delayed list. We check that its tick count is less than something, the item value of the generic list item. If it is, I guess that means the timeout has not yet expired. Then we disable interrupts. And this seems like some maybe edge case thing. The event could have occurred just before this critical section. If this is the case, then the generic list item will have been moved to the pending ready list and the following line is still valid. Okay, also the PV container parameter will have been set to null. Okay, so I guess we remove it from, maybe we remove the coroutine, I'm guessing is the sort of thing we're doing. We check whether the coroutine is waiting on an event as well. And if it is, we, I guess, remove it from the event list. We re-enable interrupts, and then we add the coroutine to the ready queue. Okay. So that's all straightforward once you don't get confused by the double negatives like I did. And then here's the initialization function. That's not so fascinating. So this looks to me like scheduling. This is the first scheduling thing we've seen. I don't know if everything is a coroutine or if there's any other scheduler, or if there's any way to influence scheduling or to use a different scheduler, but that seems to be the heart of scheduling, at least if we've seen it so far. We have a few things left. We have stack macros. I see a couple of things in the comments, in the chat, and I will look at those in just a minute. But where are we on time here? An hour and 32. Okay, so I'm going to guess these stack macros are useful for developers, but probably not super useful for understanding what FreeRTOS is about. So I'm going to ignore them. I'm going to ignore a stream buffer, and I'm not going to look closely at the coroutine implementation, although I think that's just what I did. So I guess I did look closely at it. Maybe the last thing I want to do is just look up schedule, just to make sure I'm not missing another scheduling entry point. We've got the start and end scheduler vport thing, which we saw earlier, and a bunch of implementations. And then let's try Emacs as well, since the GitHub search wasn't working the way I expected to. I assume that's because my expectations are crazy, not because they've not implemented search well. I guess I'll do schedule with no E. So a few references in timers. In fact, lots of references in timers. And maybe I just missed it in timers. Some stuff in portable, which we knew that that it was in portable. A bunch of configuration stuff in FreeRTOS.h, and some stuff in task and in coroutine. I'm going to guess the stuff in task is not the most interesting, but maybe we did miss some stuff in timers. Well, mainly in comments. Okay, so maybe we didn't. Maybe the scheduling is just all essentially in the coroutine scheduling that we just saw, which would not completely surprise me. And then in the chat, someone was asking me to find main. We can do that. And somebody else was asking me, so I pop this out and put it over here? No, I can't. Do that? No. All right. So get study learn op was asking about the main function. And then somebody whose name, unfortunately, I can't entirely see. Oh, there we go. Oh, John Wassinger says device drivers don't have a main function, just setup entry and exit points. Oh, I guess that's a reply to get study learn op. this count as a device driver? I don't know. Yeah, this is a good point. We'll search for main. This is running as the operating system, right? And it's running on microcontrollers. So the main entry point is it's like when your operating system is scheduling your program, that's the place that it calls. But like the BIOS, for example, I have no idea how BIOS entry points work. At some point, we will look at grub. And I don't know if I think the BIOS or whatever just ultimately hands it off to the operating system's entry point. And I don't know how that's done, but we'll see if there's anything main like here. And then Grossfan is saying hello, hello. Sorry that the chat, my ability to put chat on the screen is currently broken, but I'll fix that at some point. Whoops. I missed the notification here. So we'll look for main. No, don't say that. I think I just typoed some stuff. Okay, here's the, we get void main in timers. I'm going to guess that's an example. Just got to take a look at it. Yeah, seems to be some sort of comment. Then again here, there's an asterisk in front of it, which I think means it's part of a multi-line comment. So I think that we don't necessarily get a main entry point. So let's ask, I guess, Bard. Tell me about who does our new chat. I'll say, are you familiar with FreeRTOS? So tell me about the boot process for FreeRTOS. How does the device determine the entry point for the FreeRTOS binary? Okay, so this is at least what Bard claims. I don't know if this is accurate, but it's breaking it down into two, I guess, just the two stages. One is the bootloader initialization. So the device powers on, the power on reset signal is triggered. This signal initializes the hardware and sets the processor into a known state. Then we do the bootloader execution. And it starts from the code from a predetermined location in memory, typically the flash memory. This is known as the bootloader. And then initialization and setup. The bootloader performs various initialization tasks, such as initializing the hardware, setting up the stack, and loading the FreeRTOS binary into memory. And then stage 2 for entry point determination, it says the bootloader locates the entry point of the FreeRTOS binary. This is typically done by looking for a specific symbol or magic number within the binary image. And then there's some stuff about context switching, and so does FreeRTOS have a main function like you would see with C code or Java code, let's say? It does not have. FreeRTOS itself does not have a main function in the traditional sense. It does have an entry point that serves a similar purpose. The entry point is typically the first function called after the FreeRTOS kernel has been initialized. In most FreeRTOS implementations, the main entry point is defined by a symbol named _start or a main CRT startup. Okay, so let's try searching for these things. Do I still have Emacs? No, I don't. Do I still have GitHub? Maybe. Oh, I'm on the wrong. I don't know. Let's try searching for main CRT startup. We don't see that. What about, was it start? We have the command start. We have this start one, start scheduler. I guess there are enough starts. Maybe I could try. That's not going to work. What am I thinking? How about start with a space in front of it? We get start one as the only example. Just for completion, let's look for an Emacs. I'm in include. Let's try start without okay. Let's just for fun, let's try it with a space. Same thing. And then just for completion, let's try whatever Bard told me was the main CRT start thing. Nothing. Okay. And then as a last resort, we will look for FreeRTOS entry point. Start.asm. Okay, is there a start.asm? Like that. Yeah, I'm not sure. I don't see any start files, start.asm files. Maybe we can try start whatever. I'm not sure how to find the entry point for this, but there is some entry point. It might be port specific, and it's since it's going to involve the whatever chip or microcontroller you're working on. Presumably, it's however it handles booting. That has to figure out the entry point in a different way on kind of a per port basis. So I'm going to guess this is per port. And there's probably some guidance out there for how to handle that. But I'm not sure. I don't know enough about that process to at least to quickly find how that would go. But it's correct that there's no like main function in the traditional sense. And I'm going to call it a day there. That's all for me. That was FreeRTOS. I've also had a request to do, I think it's called Trampoline RTOS. And so we will do that at some point. And as I mentioned at the beginning, I am temporarily pausing new requests for videos to give myself some time to work through the existing backlog. And after once I unpause them, there will be some sort of rate limiting, possibly restricting it to a particular Patreon tier or something along those lines, just as a way of making sure that I have a bunch of stuff that I want to take a look at as part of how I'm thinking about the open source world. And I want to make sure that that's also balanced with all of the great requests that I've been getting. So that's all for me. Have a good week. Thanks for watching.